Hello everyone, this presentation by our team aims to present the thinking and decision making of our autonomous Reversi agents developed in this project. Our team developed 3 agents, each using one of these 3 technicals as co-algorithms, and chose the agent implemented using Monte Carlo tree search as the final submission. Early in the project, we considered the algorithm of breadth-first search, which is a very systematic search strategy as it considers all nodes of level 1 first, then all states of level 2, and so on. Breadth-first search is able to obtain an optimal solution at a uniform cost. It's easy of implementation, allowing the team to quickly get a usable agent. But as a blind search method, it's difficult to implement the global strategy of the Reversi game.
Our second agent uses the negamax algorithm, which is derived from the minimax algorithm. It uses depth-first searches recursively to generate the search tree and returns the score of a node. Also, alpha-beta pruning is implemented to improve the computing efficiency. It cuts off the unnecessary search nodes and branches of the tree. However, the major disadvantage of this agent is that it is not very computationally efficient. In 1 second react time, it can only search 2 layers.
Next, the AI method used in our group is MCTS. In the select stage, I choose the agent action randomly by using e-grading. It's because it spends the least time on the selection, but it still can find out the optimal action after many iterations. In the expand and simulation stage, I use breadth-first search for the next opponent action to get high reward, so that we can avoid the opponent to get this action. For the reward implement in the backpropagate stage, you can see in the screenshot, it shows the reward for different action, and agent will choose the highest reward for the next move. In the search trees, you also consider the next few action by the opponent action and our agent. There are some advantage and disadvantage for the MCTS. First, the MCTS performs a symmetry tree adaptive search space topology growth. This algorithm will receive more high reward node and more search time on the relevant part of the tree. Then, the algorithm can stop anytime and return the cover best estimate, and the search tree can discard or reuse later. The weak point for the algorithm is if the computing power is low, it may not get a high reward action due to limit iteration, so the MCTS may not get a good performance.
We compared the performances of different agents by letting them play against each other, and the results, which are winning rates, are calculated by taking the average value of 5 rounds of competitions, and each round contains 100 games. This table illustrates that different agents have their own advantages, and no single agent can outperform both other agents. The BRFS agent won about 70% of its games when facing the MCTS agent, while it lost about 88% of its games against the negamax agent. And the MCTS agent yielded a 75 winning rate facing the negamax agent. After comprehensive consideration, we finally chose the MCTS agent to represent our team for the following reasons. Firstly, the MCTS agent performed relatively consistent when playing against different agents, which proves that it is the most robust one among all the agents. And secondly, the MCTS algorithm does not require any knowledge of the given domain or specific strategies to make reasonable decisions. This algorithm can work effectively with only the basic rules of games.
In the future development, we need to find a way to reduce the demand of the computing power for one iteration in the MCT race. The first method is we use the domain knowledge in the Reversi game to figure out which move can get high reward. Second, we need to build a better reward function. Then the MCTS can find the highest reward action earlier. The third point is the earlier determination on the simulation stage. For example, only one node can sample to an arbitrary depth, and instead evaluate like a minimax search so that it can terminate faster in the simulation stage.